Water is essential, but delivering it with constant pressure requires a feat of civil engineering, which is the elevated water tank. For our project, we analyze the elevated water tank right here at Jalan Chari HM to see how fundamental engineering principles keep massive structures in the air. Holding thousands of liters of water high in the air is a massive challenge. This structure constantly fights against intense forces, including the deadlock of its own concrete, the lifeblood of the water, and the outward hydrostatic pressure. Without any careful analysis, these locks can lead to catastrophic structural failure. To ensure its safety, our project focused on 3 goals. First, identifying these critical loads. Second, calculating the support reactions using free body diagram. And third one, evaluating the tank's overall static stability. By bridging classroom theory with real-world infrastructure, we can guarantee this vital utility system remains safe. Now, let's move on to chapter 2 for the literature review.
Now, let's move on to chapter 2, which is our literature review. In this section, we look at the core ideas behind elevated water tanks. We want to understand how these structures behave on how they safely handle different forces. What exactly is an elevated water tank? Simply put, it is a huge water container built high up in the air. It stores water at head so that gravity can naturally push the water down with enough pressure to reach everyone's pipe without relying entirely on pumps. Because a massive, heavy amount of water sits directly on top of tall, thin support frame. Realizing its stability is incredibly important. To make sure the tank stays safe, we have to identify all the loads or forces acting on it. There are 3 main types. First, it is the self-weight of the structure. This is the permanent heavy weight of the concrete walls, the base slab, and the column pushing straight down. Second is the water weight. The massive amount of water inside pushes down on the floor, but it also pushes sideways against the tank walls. Third is the wind load. Because these tanks are built so high off the ground, so winds can push against them from the side.
To make these forces easy to see and calculate, we use a tool called a free body diagram or FBD. This is just a simplified drawing of our water tank that maps out every single push and pull acting on it. It helps us see exactly how the downward gravity loads and the sideways wind forces interact with the structure. Next, let's look at how the tank connects to the ground. We assume the columns are rigidly anchored into a heavy, deep foundation, which we call a fixed support. This fixed base locks the structure in place and keeps it stable in 3 ways. First, it pushes straight up to stop the heavy tank from sinking into the dirt. Second, it fights back horizontally to stop the wind from sliding the tank sideways. 3, it acts like a tight clamp twisting back to stop the entire tower from tilting over when the wind blows hard. Finally, for the tank to stand completely still, everything must be perfectly balanced. This is called static equilibrium. The total upward push from the ground perfectly matches the total downward weight of the tank and water. The sideways grip of the foundation perfectly balances out the push of the wind. When the wind blows from this side, it tries to tip the tank over. To stop this, the columns on the side will away from the wind take on a tighter squeeze, while the columns facing the wind get a bit of relief. This smart distribution of weight keeps the entire system completely still, safe and stable.
Okay, for my part, I will explain the lateral water pressure acting on the wall of the elevated water tank. When water is stored inside the tank, it creates hydrostatic pressure that increases with depth. In this project, the water depth is 2.5 meters and the maximum pressure at the bottom is 24.53 kN per meter cube, while the pressure at the surface is 0. So, for the resultant lateral force acting on the wall is 30.66 kN per meter width, acting at 0.833 meters above the base. So, in conclusion, the tank wall must be designed to resist this pressure to ensure the safety and stability of the elevated water tank.
Now, let's zoom in closely to the tank wall itself. By looking at its specific free body diagram, FB, Firstly, we can see the exact forces acting on this part of our 10-meter wide tank. First, there are two main forces pushing straight down because of gravity. First, the permanent weight of the concrete wall itself, which is 495 kilonewton, and the massive weight of the stored water, which pushes down with 1957 kilonewton. Together, that makes a total downward weight of 2452 kilonewton. Secondly, we have a horizontal force. The water inside pushes upward against the wall in a triangular shape. It starts at zero at the top of the surface and gets stronger the deeper it goes, reaching a maximum push of about 30.66 kilonewton per meter at the very bottom. This sideways push creates a heavy tilting effect on the wall. To keep the wall perfectly safe and still, the bottom supports pipe back in three ways. It pushes straight out to hold up the heavy weight of the concrete and water. It also pushes inward to stop the water from shoving the wall upward. And it acts like a tight clamp, creating a resisting moment to stop the wall from tilting over. This perfect balance keeps our tank wall completely steady, upright, and safe.
This section presents the equilibrium analysis of the tank wall under hydrostatic pressure. The wall is assumed to act as a vertical cantilever fit at the base. The hydrostatic force acting on the wall is 30.66 kilonewton per meter, which is balanced by an equal horizontal reaction force at the base to maintain equilibrium. The overturning moment caused by this force is calculated as a 35.54 kilonewton per meter. Therefore, the wall is able to resist both the lateral force and the overturning moment, ensuring the structural stability of the water tank.
I am Nur Shakirin. For my part, I will explain the calculation of centroid for the wall section of the elevated water tank. In this project, the tank wall is assumed as a circular hollow section. This means we calculate the outer circle first and then subtract the inner circle because the middle part is empty and filled with water. The outer diameter of the tank is 10,090 millimeters, while the wall thickness is 250 millimeters. So the inner diameter becomes 9,590 millimeters. To find the centroid, we use the formula x bar equals to ax over total area and y bar equals total ay over total area. Since the wall has a uniform circular shape, the centroid is located exactly at the center of the circle. Therefore, both x bar and y bar are half of outer diameter. So, 10,090 divided by 2 gives 5,055 millimeters. This means the centroid of the tank wall section is located at the center point, which is 5,055 millimeters from the x direction and 5,055 millimeters from the y direction. This centroid is important because it helps us to understand where the center of gravity of the wall section is located, and it is also used for the next calculation, which is the moment of inertia.
Now, let's look at the moment of inertia of the wall section. To understand how the tank wall resists a lateral water force of 30.66 kilonewton per meter, this geometric property measures the wall direct structural resistance to bending. The wall forms a hollow circle. Using the formula of 1/4 pi r power of 4, we take the large outer concrete circle and subtract the inner empty space. This gives us a net moment of inertia of 93.6 times 10 power of 12 millimeter to the 4th power. Because of a circle is perfectly symmetrical, Ixx and Iyy are identical. This massive uniform value proves that our concrete wall is geometrically optimized to handle weight forces safely from every single direction.
For the discussion, the structure analysis was conducted to the performance of elevated water tank under the various loading conditions. The tank has a safe weight of 994 kilonewton and water load of 1957.1 kilonewton. The maximum hydrostatic pressure is 24.53 kilonewton per meter square, generating a lateral force of 30.66 kilonewton per meter. The structure is supported by 8 columns, each column carrying 268 kilonewton. Based on the result, the tank is stable, safe and suitable for the long-term water storage.
In conclusion, this project successfully analysed the static behaviour of the elevated water tank by identifying the loads acting on the structure and applying equilibrium principle. So, the results show that the tank is stable under the assumed loading condition, with the stored water contributing the highest load. So overall, this project helped us understand how static concept can be applied in real civil engineering structure.